So this is the outline for chapter 27. We will talk about the single loop circuits and then the multi-loop circuits. We'll also talk about the ammeter and the voltmeter. And then finally, we still talk about something like the RC circuit. RC circuit. Okay, so let's see. Okay, so here it says the single loop circuit. So you can see here, we have a battery here. So a battery, you can also regard it as an electromotive force. And and here we have a resistive circuit in series. So it is just a single loop. We connect the battery to the resistor and then connect the other end of the resistor to the battery. So it's just a single loop. Okay, so it says to produce a steady flow of charge, you need a charge pump or a device that by doing work on the charge carrier and blah blah blah. We call such an EMF device or a battery. So the device is said to provide an EMF E, which means that it works on charge carriers. I think I can just skip it because it's just mentioned that we connect this positive side to a resistor, this negative side to another end. So nothing special. Okay, so here it says an EMF device does work on charges to maintain the potential difference between its output terminals. So the voltage or the potential difference between this side and this side will be E. Okay, so if dW is the work the device does to force the positive charge dQ from the negative to the positive terminal, then EMF of the device is dW dQ. So this is the definition. dW dQ. Okay. So an ideal EMF is one that lacks any internal resistance. The potential difference between its terminal is equal to the EMF. So actually, I would say for this like battery or the EMF in circuit theory, sometimes we will just write it as this one. So this one, the long line stands for the positive end, and then the short line stands for the negative end. And sometimes I will draw it like this, a voltage source or Vs or E or whatever, something like this. So this is also the circuit symbol for the battery, or we will call it independent source. Independent voltage source. Okay. Sometimes I draw it like this, so you should know for this one, or this one, they actually means the same thing. Okay, so and here is talk about the ideal EMF device, which means that there is no resistance in series with this voltage source. And a real EMF device has internal resistance. To the potential difference between its terminal is equal to the EMF only if there is no current through the device. So if we try to draw, so this is the ideal EMF, which means there is no internal resistance. So let us denote this is the potential difference V, and then this is the current going through it, and then if we try to draw this out, so if the x-axis is the current, and then the y-axis is the voltage, then in this case this line should be a horizontal line, which means that it does not depend on the current. we have a fixed voltage across this ideal EMF. So this is maybe we can say this is Vs, so Vs like this, or also, sorry, should be V, and then this is Vs, it should be something like that. Or if it is a real EMF, it says it has some internal resistance, but we will somehow draw it like this is a ideal EMF Vs, and then in series with a resistor R, let's say Ri, something like that. Okay, so this is the whole thing is the real EMF. It's the whole EMF. So let's denote this V. This is the V. This is the V, and this is still the I. This is still the I. Okay, so in this case, if I is zero, then this point is still Vs. This point is still Vs. But if I is positive, there will be voltage drop across this Ri. The voltage drop of this Ri will be nothing but I times Ri. So according to the Ohm's law, I times Ri. And then the current is going from bottom to top. So this is positive, this is negative. And in that case, this line is not horizontal with a negative slope. The slope of this line should be a negative Ri. Negative Ri. Because this line is actually V equals Vs minus Ri times I. Okay, so in high school you should learn the analytic geometry. So this is the y-intercept, this is the slope. This is the slope. Okay, so this is the difference between the ideal EMF and the real EMF. Okay, so here it says how to analyze this single loop circuit. So in circuit theory, we seldom use the energy method, but yeah, when I prepare this course, in this chapter, it just look into this circuit in a very physics way. So it also mentioned about the energy method, which is quite interesting. So let's see what it is. So here we have a battery. We have a battery E. E is the potential difference between this node and this node, and then it is in series with the resistor R. So it is just actually the same as the previous circuit. And for when you try to solve a circuit, you can just pick any of the node and then you define it as the ground. Then it will make things easier. So let's see how we can use the energy method to analyze this circuit. So although it's quite stupid, but actually we can also use this energy method for later circuit, which will give you some interesting insight. So let's see. So here, P equals IR squared is actually the power dissipation of a resistor. So let us tell us that in a time interval dt, an amount of energy given by I square RT dt will disappear in the resistor. Actually, this resistor consumes this energy, I square R dt, because P is the power. So power times the time fragment will be the energy fragment dissipate in a small time interval. So will appear in the resistor, and then as thermal energy. This energy is said to be power dissipate, which means consumed by this resistor. So because we assume the wires to have a negligible resistance, no thermal energy will appear in them. So we assume that this wire is pure non-resistive. The resistance of this wire and this wire is perfectly zero. Or in circuit theory, the concept is called a lumped. It's called lumped circuit. Lumped circuit. So practically the wire should have some resistance, but we count all the resistance to be at the resistor, and then we just count this wire to be without any resistance, to be a perfect conductance. So which will simplify our calculation. So we usually do that. We just assume the whole line has the same potential, has the same electric potential, and then all the resistance counts on the resistor. And actually, usually the resistor value could be quite large comparing with the wire, so it is reasonable to make this assumption. Okay, so yeah, so during the same interval, a charge dq equals I dt, because the definition is like I equals dq dt. So we just move over dt. So we have a dq equals I dt. We'll have moved through a battery B, and the work that the battery we have done on the charge is this expression dw equals E times dq. E times dq is just the definition in the previous page, and then dq is actually I dt, so we just plug this one here, so we have a E times I times dt. Actually, if you still remember, for the battery, the power consumed by the actually the power of the battery will be V times I, or here the power is E times I. So dW will be the power times the dt, so it is nothing but E times I times dt. Okay, so from the principle of the conservation of energy, the work done by the battery must be equal to the thermal energy that appear in the resistor. So actually this one equals this one. So we have a EI dt equals I square R dt, and then finally you come up with this I equals E over R. So which is nothing but the Ohm's law. So actually here E, so we can see suppose this one is 0 volt, and then this node should be E volt. Okay, so across this resistor, the potential difference is E, so the current should be E over R. I equals E over R, or E equals IR. So it's nothing but the Ohm's law. So it feels like quite trivial. Okay, so after making a complete loop, so this is the other method called the potential methods, which is generally used in circuit theory. So in circuit analysis, we seldom use this energy method, but yeah, we usually just go into the circuit and then use the potential method. Sometimes we'll use the KCL, and sometimes we'll use the KVL. The KCL stands for the Kirchhoff current law, and the KVL stands for the Kirchhoff voltage law. So the KCL is about the current. Actually, we have, I think I have mentioned it in chapter 26, and then this one is about the voltage. Okay, so in the figure, let us start a point A. Whose potential is VA. So it didn't assume this one is a ground. So it just assume the voltage here is VA. So which is, yeah, you finally you find out that this VA will just cancel. So it's reasonable to just assume it to be 0. So but here it's just mentioned like this. So it says without assuming this to be ground, so it just assumes this potential is VA here, and then mentally walk clockwise around the circuit until we are back at the point. So actually this potential method is actually the KVL. It's actually the KVL. So it says this is a complete loop. So you can just start from this point and then going like clockwise or counterclockwise. It depends, doesn't really matter. And then after going for the whole complete loop and go back to its original point. So the potential changes over the complete loop should be 0, because when we talk about this circuit, it don't involve any magnetic flux changing, so it doesn't really apply the Faraday's law. And here we of course assume that E dot ds to be 0 for this case. Okay, so here yeah, so our starting point is is at the low potential terminal of the battery, and because the battery is ideal, blah blah blah, and then so starting from this point, the potential is VA, and then going to here we should add E to it. So we have the second term plus E here, and then we keep going further, and then this is a perfect wire, so we don't have potential drop or potential gain. And then for here, for this path, the current is going from top to bottom, from top to bottom. And then this is a resistor, so it will have a voltage drop I times R according to the Ohm's law. So we have a minus sign here because it is a voltage drop. The current is going from top to bottom, so this end should be high, should have a high voltage, and this side should have a lower voltage or lower potential. So we have to minus this one. We have to plus for the EMF and then minus for this one. And of course we know the current is going clockwise. So VA plus E minus IR. Then we go to this point, and then this is a perfect wire, so we go back here. This node should be VA. So finally you find that VA and VA will cancel each other. So finally it turns out to be E equals IR or I equals E over R. So which is actually the same as the previous equation. Okay, so this is quite trivial, and then here is summarized some rules. So the first one is called the loop rule. So the algebraic sum of the change in potential encountered in a complete transversal of any loop of a circuit must be 0. So usually I would just call it the KVL, Kirchhoff voltage law, and then here the resistance rule. So for a move through a resistance in the direction of the current, change in potential is minus IR. The opposite direction is plus IR. So this is nothing but the Ohm's law. And then for the EMF rule, for a move through an ideal EMF in the direction of the arrow, the change is plus E, and in the opposite direction is negative E. So the difference here is when we talk about change in potential is negative. This is a negative value. This is a plus value. And for opposite direction, this is plus. This is negative. So the sign between the resistance rule and the EMF rule will be opposite to each other. Okay, so you can do more practice, and then you will not make mistake to the plus or minus sign. Okay, so here it talks about the EMF with internal resistance, which means this is a real battery, and then we have this one. Okay, so here it shows a real battery with internal resistance small r wired to an internal resistor, blah blah blah. Okay, so yeah, so actually to really solve this circuit, we can just consider the total resistance. The total resistance of this circuit is small r plus capital R, because they are in series. So which is like we have a, which is actually equivalent to, we have an ideal battery, ideal EMF, and then in series with a resistor which is R plus capital R. So this is, in this case, this is nothing but I equals E over R plus capital R, or capital R plus R. Okay, but here it try to go through it more deeply, which is like it try to cut it out, not physically cut it out. It just try to mention it like this is point A, this is also point A, and actually it's still connecting, but it just try to explain it to be a one-dimension circuit, and then try to connect it here to really express how the potential is changing along the path. So still starting from point A. So the potential here is VA. Okay, so here we try to go through this EMF E, and then it is in the direction. So we need to add E to it. So it jumps from VA to VA plus E, and then of course the difference between here is E. And then the next step is to go through this internal resistance small r. So here the current is going from bottom to top, and then we also go from bottom to top. So we need to minus this IR. So here we have the voltage drop small IR. So we need to subtract it from this value. So this difference here is small IR. And then we keep going further until here. So we need to also go through this resistance capital R. And then so we also need to go from top to bottom. So we need to subtract I times R. So this is I times R. And then this is already VA. This is already VA. So we go back to VA. So which means that we start from VA going up, going down, back to VA again. Okay, so this is still a single loop circuit. Okay, so here it talks about the resistance in series. We have not talked about it yet. We only talk about the capacitance in series or capacitance in parallel. So here, just talk about the resistance in series. Okay. So actually, we don't talk about the resistance in series yet, but I suppose you have learned it in high school. So here it says, if we have three resistance in series, resistor in series, R1, R2, and R3. Okay, so we can simply apply the KVL. We start from here. We can just assume this point to be the ground. Okay, so this is 0 volt, and then we plus E here, and then going to here, it should be R1I, and then with a negative sign, and then going to here, minus I R2, minus I R3, and then going back to the original point. So it should be like this. Okay, so up to here, it already forgot the VA, because he already know that the VA should be cancelled. Okay, so we can just assume this point to be the ground. So we have E minus IR1 minus IR2 minus IR3 equals 0, and then we move over this term, and then we just divide R1 plus R2 plus R3 on both sides. So we can see I equals E over R1 plus R2 plus R3. Okay, so when comparing with this circuit, this is a single battery with the same potential difference, and then this one should be equivalent to this series resistance, and then we should get I equals E over Req. So this Req should be actually the same as this R1 plus R2 plus R3. So we get this, and of course for N series resistance, we should just add them together. Okay, so so this is series resistance. We just add the resistance together. And then for here, it talk about the potential difference across real battery. Okay, so here, actually I just mentioned it already, and here you can see the current is I, and then we start from here to here. Actually, we consider the potential difference is from this node to this node. This is the V across the real battery. And then this is E. Consider this E is an ideal EMF. So we start from this point going to here. So we add E, and then we minus IR. So E minus IR will be the potential difference from this point to this point. So we have V equals E minus IR. So if I equals 0, then V is nothing but E. But if I is positive, then the batteries will drop. I mean the potential difference across the real batteries will drop. Okay, so here is also mentioned that grounding a circuit. So grounding a circuit usually means connecting one point and only one point in the circuit to a conducting path to the earth surface, which means that you consider that point to have a 0 volt. Okay, so and then the power of the EMF device will be I times E. So it's nothing special. I times E or I times V. Okay, so here we have a sample problem. So which is quite easy. So here it says the EMF and resistance in the circuit have these values: E1, E2, R1, R2, and capital R. What is the current I in the circuit? Current I. So it already defines I in this direction. Okay, so let's see. We can just try to use the KVL to write out an equation, and then we can try to solve what is I. So let us start from this point A. And then we go in clockwise direction. Okay, so starting from this point going to here, this EMF is has the opposite direction with how we move. So we should have negative E2 here, and then we keep going forward across this R2. R2 has the same direction as the current, so it should be minus IR2, and here minus IR, and then from B to here it should be minus IR1, and then from here back to point A, it should be positive. It should be positive because this direction is actually the same, has the same direction as the EMF. So we have a plus E1 equals 0 because we go back to the original point. Okay, so here we can just collect the terms, these three terms together, and then we move over the E1 and E2. So we have or maybe we can just move over I because they are negative sign. So we have E1 minus E2. E1 minus E2 equals I times R1 plus R2 plus capital R. So we can get I equals E1 minus E2 all over R1 plus R2 plus capital R. Then we can just plug in the values. 4.4 minus 2.1 all over 2.3 plus 1.8 plus 5.5. So this is nothing but 0.2408. So far, any questions? Okay, so for part B, what is the potential difference between the terminal of battery 1? Which means that from this point to this point, we would like to find VAB, which means VA minus VB. The potential difference between them. Okay, so let's try VAB. VAB should be start from this point B and then going in this direction. So this is going this way. So this direction is actually the same as so actually here we know the I is a positive value. The I is a positive value. Okay, so maybe I can just mention it a bit. Here it already tells you that I should be clockwise, but originally if it doesn't tell you, you don't necessarily know what is the direction of the current, but you can just assume the current to be in either direction. Just say to the right side, and then you do all the calculation, assuming that I is going from left to right or going clockwise. Then finally, if the answer is negative, then the direction is reversed. Just say if originally we assume the current I is going from right to left, then finally you will come up that I prime to be negative 0.240 to the left side, which means that it should be going to the right side as a positive value. Okay, so here VAB. Okay, so actually we already know that I equals 0.2408. Okay, so here from point B going across R1, it should be minus IR1, because this direction is actually has the same direction as the current. And then from this point to this point, we should add E1 because these two arrows are in the same direction. Okay, so here we have a minus 0.240 times R1 is 2.3 plus 4.4. So this is nothing but 3.8 volt. Okay. Okay, so here it also mentioned about the junction rule, and of course I will just call it KCL, Kirchhoff current law. Kirchhoff current law. So the sum of the current entering any junction must be equal to the sum of the current leaving that junction. Actually, we already mentioned it in chapter 26 as the Kirchhoff current law. Okay, so the current going into the junction must equal to the current going out. Charge is conserved. Charge is conserved. So usually this KCL is mentioned like this: the sum of the current entering the junction must be equal to the sum of the current leaving that junction. But in my experience, I will usually consider the current is going out and then we sum it to be 0, which makes things easier. Just say for example, this one we make it. So let us try to consider, let us say point D will be the ground. Then we will be able to find the current, or actually solve this circuit. Okay, so here we can see, other than this ground node D, we have 3 nodes, A, B, and C. But actually, this point A has only 2 wires, which means that this current is going like this, and then this current is going like this. So the only point we concern is point B. If we already know the voltage VB here, then we can quickly find A, because VA is nothing but VB plus E1, and for this point C, VC is nothing but VB plus E2. So to solve this circuit, the only concerned variable is actually VB or VA, which means that these 3 variables, you only need to know one, and then you can quickly find the other 2. Okay, so let's try. So let's call it VB here, and then we consider the current going out. The current going out should sum up to be 0, or going in, but usually I try to use going out. So let's determine what is the current I1 here, and I just try to make it like I2 going from top to bottom. Okay, so here this is I1, this is VB, so this VA should be VB plus E1. And according to Ohm's law, the voltage difference across this R1 will be VB plus E1 minus 0. So VB, and maybe I can just write it like I1 plus I2 plus I3 to be 0, because I1 is going to this side, I3 is going from top to bottom, I2 is going from left to right, like this. So I1, I2, I3 are all going out from node B. Okay, so I1 plus I2 plus I3 should be 0. Okay, so I1 here is VB plus E1 over R1. And then for I2 is this current, And then we should determine the current according to this resistor. And then we have to know this potential VC. So VC here should be VB plus E2. Don't try to consider what is the current going through this battery independently, because as I mentioned, for an ideal battery, you cannot know the current, because this is just say E1, this is the current, this is V. So no matter what the current is, the voltage or the potential across this EMF is the same. So you cannot find the current by itself. You should try to find the current from the passive element, like the RLC. Okay, so here VB plus E2 over this resistor, and this is ground node. So the current I2 should be VB plus E2 over R2. And then for I3, this is VB, this is ground, so this current is VB over R3, like this. Okay, so we can just collect all the terms. VB times 1 over R1 plus 1 over R2 plus 1 over R3 equals negative E1 over R1 plus E2 over R2. Okay. Actually, this term is this term, this term is this term. Okay. So here we can find VB to be negative E1 over R1 plus E2 over R2, or over 1 over R1 plus 1 over R2 plus 1 over R3, like this. And actually, when you already find what is VB, then you can quickly find out what is VA, what is VB, and all the current. Okay. So far, any questions? If no question, let's have a 10 minutes break.